1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So let's see if that works. Yes, we see something. So we're still just testing it. That looks okay. The slides are here. So we're about to start, but we still need to test everything. A ještě pustit aplikaci. To je, teď jsem si zrovna vzpomněl. Jo, takže tu minulou mažu. Radši, ať se to nesplete. Tak. Start recording. Tak tohle už nahrává. Tak, tohle je dobrý. A když si sednu, tak tam ani nejsem vidět. Jo. Aha. Takže ještě furt to něco ruší. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3.
Bylo to asi z těch
zásuvek, nebo těch zásuvek. My jsme museli kdysi volepovat nulák s izolepou, ale...
Já si myslím, že to je tím, jak tam bylo toho zásuvce.
Jo, no. Něco se nabíjí, nebo tak něco. No. 1, 2, 3, 4, 5. Jo, vyberete zvuk ještě takhle bokem prostě.
Jo, vždycky, no.
Nebo to je prostorový teda jenom.
Tohle je záloha, kdyby...
No, jako záloha prostoru prostě celýho. Protože to mám svoje mikrofony. Ne. Rozvedený, jo. 1, 2, 3. 1, 2, 3, 4. The subtitles of of Czech being transcribed are beautiful. But I hope that you can also, those of you who are attending, that you can already hear me. And I hope the sound loudness and all that is okay. Jo. Správně, no. No, právě. To se vůbec nedivím. One, two, three, 4, 5, 6. 1, 2, 3. 1, 2, 3. Že něco je pořád ještě jinak, jo. Teď už tam ten zdroj není, no. No třeba jsem já na jako stejném okruhu zásuvek s něčím tady ode mě, že jo.
Já jsem to teď neměl ani zásuvce.
Jo.
Ale asi pustím jen tak samotný.
Jo, jako ten prostorový právě, no. So in the meantime, I can tell those of you who are attending, and I saw there are 4 of you, that's great, that today I'm going to record 2 lectures in a row, as you have read in the document, and next week there will be, the session will be streamed automatically, I guess, so I'll try. And I'll answer your questions for the next lecture and also for this lecture in the document. So I will answer your questions for today probably in the afternoon, and for the next week I'll answer them next week sometime after the lecture. So I will paste again the link to the YouTube video to the document that you're looking at now, but I actually recommend to watch it only in a week from now, because both of the lectures are packed with contents, and it would be too much for you to digest. And let's see if it will be too much for me to present, or if I can manage. Yeah, tak. Říkám se, no. Yeah, so that's one more recording device, because everything is unreliable, and I'm happy to see that it's happening also to professionals and not only to us. That's about 1, 2, 3, 4. Am I saying something? And yep. So we are probably very soon ready to start. So yeah. Yeah, okay. So the application is running. I'll double check. Yes, it says 4 minutes. And the slides are ready. The audience is ready. Subtitles are getting there somehow. And one of the cameras still needs a little adjustment, and then we'll go. Tak. So, can we start? Just a second, okay. The slides are on the web, and also the slides for the next lecture are already under the link on the web page of the seminar. But I deliberately left the date on the web page so that you are not too curious and not looking at the slides already this week. Well, you can if you really follow the next session from 10:40 today, then you can download the slides from the web page, even though the date says it will be next week, or last year it was. Okay, so that's it. Let's get started. So good morning again. Welcome to our next lecture on machine translation, and today we're going to discuss morphology in machine translation. I'm Czech, and that's maybe the main reason why I'm so focused on morphology, because Czech is a flective language and it's highly complex, and we'll see some examples of that. And when we're translating into Czech, we need to deal with this rich morphology. So in the lecture today, we'll first talk about the problems caused by rich morphology. Then we'll illustrate the combinatorial explosion that happens in Czech because of the abundance of available word forms. And then we'll mention that the scores could be much higher if we ignored the word forms. So if the final reader was not a human who needs all the words in their correct forms, but if it was a machine, if we ignored all the problems, all the bad form choices, then the scores would be much higher. So we'll start with this summary of problems, and then we'll cover both the classical statistical machine translation, specifically the phrase-based machine translation, and how that deals with morphology. And then we'll also move to neural MT and discuss how rich morphology is solved by neural MT. So the complexity of morphological system, so the system of word forms and word formation, can be illustrated by comparing Czech to English. So if you are a linguist, then you would know that in Czech, to describe, to select one of the particular word form of a word, you need some morphological tag. And that morphological tag uniquely describes what the form will be. And across the language, across all the parts of speeches, there are more than 4,000 Czech tags possible. While in English, linguists are happy with just 50 tags. That means that the word form variety in English is so little that the linguists do not deem it important to record it in a formal device such as the tags. And this 4,000 in Czech, that's in theory, that is what the morphological system allows, like what is defined. And if you take a big corpus, then you really see these tags. So you will see more than 2,000 tags in a big corpus quite easily. This rich morphology is there for a reason, or put in other words, the users of the language make use of that. The rich morphology allows people to shuffle the order of words in the sentence in many ways. That's because the syntax of the sentence is more reflected by the word forms than by the order of the words in the sentence. So this rich morphology comes normally or very often with the free word order across all the languages. People simply follow the forms of the word to reconstruct the meaning of the sentence. In English, you don't have this indication of what belongs to what, and you have to rely on word order much more. Here's also a comparison of from a particle power corpus. This is a corpus of news commentaries. It's not too big. It's 55,000 sentences, and the number of sentences is well, identical in the two languages, but the number of tokens will not be identical. In English, you will have slightly more tokens. That's because English uses articles and we don't have them in Czech. But if you now collect all the word forms that are visible in this corpus, you will notice that the vocabulary size in Czech is more than double the vocabulary size in English. So these sentences were saying the same thing in both Czech and English, and yet Czech needed double the vocabulary size. If you lemmatize, if you move from word forms to just the base forms of all words, then the vocabulary size becomes much more comparable. So that confirms again, yes, these two sentences were saying the same thing. They use the same words, but in Czech, to put them in correct grammatical structure of the sentence, you need to inflect them. You need to change the words in some way. So when we are translating into Czech, we have to face this complexity. As I mentioned, we have many forms. So for nouns and adjectives, for example, this is reflected in the fact that we have 7 cases, 4 genders and 3 numbers in Czech. And then we have also similar complex setup for verbs. So when you are translating a sentence, you have not only the choice what the word means, so this I saw 2 green striped cats, this saw can be either a chainsaw or the verb seeing, so this is 2 clearly distinct words, and you are choosing the meaning of the word saw. But in Czech, in addition to that, you also have to choose the particular ending of that word. And this is where the combinatorial explosion comes. Of these combinations, only very few are actually correct. But you have to have some good understanding of the grammar in the system so that you are able to pick the right combination. There is also morphological explosion in other languages. In German, words are put together. So this Rindfleischetikettierungsüberwachungsauftragsübertragungsgesetz that was almost voted to be the word of the year, but the word millennium then won for some reason. So this word is a law on beef labeling duty, and Germans are happy with that word written without any spaces. If you have to translate this word, you have to break it into small pieces. And if you are expected to produce these words, you have to really be clever in your system so that you can mimic what Germans normally do. The agglutination is not compounding. That's another phenomenon in word formation. In agglutination, the stem of the word, the base meaning remains the same, but you are using many suffixes, prefixes, infixes, and other modifications of the word form, so that you express some variations of that meaning. So I don't speak Finnish or Hungarian, but I found somewhere that this istua is to sit down, and with some prefixes and suffixes, you can create a single word which has the meaning, I wonder if I should sit down for a while. In Czech, we have a little bit of this with repetitiveness, but Czech is more into endings of words and agreement, grammatical agreement. So when you're translating into such a morphologically rich language, and you use some simple, the baseline machine translation evaluation method, such as the BLES score that we discussed, then this method will focus only on the word forms, whether you have generated the right word forms. Obviously, if you make any error in the ending, then you do not get the credit, so that suddenly the whole word is counted as wrong. This reflects in the generally lower scores that you are getting for morphologically rich languages compared to English. And also, if we would ignore the problems in morphology, the scores would jump higher. So, put in other words, if we ensured that our systems produce perfect word forms, they always make the right choice, the BLES scores could increase up to 8 points, for example. That was back then in the phrase-based machine translation era. Yeah, so how do we handle morphology in phrase-based machine translation? If you remember, phrase-based systems have two major components. One of them is the translation model, which is based on parallel data, and one of them is the language model, which is based on the monolingual data. And there is then the global search, which uses the sentence, the small pieces to build complete sentences. And I've already hinted a little that this global search is complicated because you have many more options to choose from. So this search space is larger. But let's now talk about the increased complexity in the language modeling and also in the translation modeling. So you are now trying to translate the sentence that was in the previous example. I saw 2 green striped cats, and you are choosing which word forms should be used to translate these 2 green striped and cats. All these numerals, adjectives, and nouns have many word forms in Czech. And if you were a native speaker and you considered this candidate dvou zelená pruhovaný kočkách, you would immediately hear that this is garbage. This doesn't fit together. This is not a noun phrase at all. If you read the other candidate, dva zelené pruhované kočky, then you would be happy for the first 3 words that perfectly fits together, but then the last word doesn't agree with them anymore. And if you read the last 3 words, zelené pruhované kočky, then again you would be happy. So this is a sequence of 4 words in a row, and all the triples or the trigrams here are okay, but the foregram is wrong. And then we have 2 examples of the good cases, nominative and accusative, and then correct dative. So here we see that the trigram language model is too weak to ensure the agreement. We need to use a foregram so that we disregard the second example, which is trigram-wise correct. But this is full words, fully inflected word forms. So in order for your language model to be able to choose between the second line and the third line, you would have to have a corpus which talks about all colors and all types of striping of all animals. And only if you have all these combinations and you see them in all cases, then the language model will have sufficient data to select the good combination. So you're not a native speaker, it's better to highlight the problem with the morphological text. So these are very simplified morphological text. The first example, dvou zelená pruhovaný kočkách, the garbage thing, is visible for you because now the labels, the morphological text, are distinct. For each word, there is a different morphological tag. And if those words were agreeing together to form a noun phrase, then there would be the same gender, number, and case used throughout that phrase. So that is the example of the second translation, dva zelené pruhované kočky. Here, one option is to understand this word dva and zelené as masculine nominative, and the 3 words in a row are an agreeing sequence of words. The second triple, zelené pruhované kočky, that is perfect feminine noun phrase, but there is no way to understand dva as a form of a feminine, and there is no way to understand kočky as a masculine. So there is no way to put these 2 trigrams together to form a valid foregram. Here is a phrase which has 4 words and that are agreeing, but I'm highlighting here the morphological ambiguity. The forms are dvě zelené pruhované kočky, and you still don't know whether this is the nominative or the accusative case. And to choose the case, you need to look around actually for the verb to see how this 4-word phrase was used. Here is another example, a phrase which is 4 words and it's totally unambiguous. We know that this is the dative case. So now what are the advantages if we modify our language models so that they don't look at word forms, but instead they look rather at the morphological tags? So language model has a purpose in the machine translation system, and the purpose is to choose the better combination of words, the better sequences of words. And it compares all the possible translation candidates. So if we're considering the probability of the bigram dvě kočkách, which is wrong, that doesn't agree, versus the probability of the phrase dvě kočky, which is linguistically, grammatically correct, there is the agreement, then a reasonable language model trained on sufficiently large data would know it, but we would need to see all the combinations of the cases and numbers and genders of this pruhovaný, the striping thing, and kočka, the cat. If we instead look at the morphological tags, we can simply observe on any combination of any adjective and noun that it is a bad idea to put a feminine adjective in nominative in front of feminine noun in locative, another case. And it is much better to have these two words in agreement with respect to the gender and case. So these probabilities that are trained on morphological tags will be observed on many more instances of any noun and any adjective, and therefore they will be estimated much more reliably. So this is where it helps. I would like to highlight that the move towards the morphological, the language model based on morphological tags does not help in all the cases. If you are asking what is more probable, whether dvě zelené or dva zelené, which is 2 good phrases, then this, in terms of morphological tags, converts to the question of comparing the probability of sequence of 2 words in feminine nominative or masculine nominative, and choosing what is more probable, whether feminine or masculine nouns. That doesn't make any sense. So that was a bad question in both the case of forms and morphological tags. So here the language model will obviously not help. But we are still getting the benefit that the vocabulary size of these morphological tags is much smaller. We don't have the 2 million of word forms that I mentioned in one of the previous lectures, but instead we have only the 4,000 morphological tags. And with this smaller vocabulary, we can afford to use much longer n-grams. So we can use 7 grams of word forms, and that gives the system quite a power about the overall grammatical coherence in the sentence. So that was the problem of rich morphology for language modeling, and now the problem for the translation model. So in the translation model, you have to propose what word forms will be used, and these are then scored and compared and selected for the final choice. But rich morphology demands to use much larger data. So if we are to translate the English word phrase kneecaps, then the Czech translation is češky. But this word has to appear in all the cases and all the numbers. So kneecaps is actually the plural form, and it has these 7 cases. You see the forms here, češky, češek, češkám, češky. In some cases, the form, the surface form of the word is identical for multiple cases. So češky can be both nominative and accusative, and also the vocative case. So as soon as you see češky, then technically you see it in all the 3 cases. But not necessarily, because the other words in the sentence will indicate that this is not in vocative but in nominative and so on. But for some of the word forms, for cases like instrumental, you really have to wait and gather much larger data. So in order to be able to say in Czech what's wrong with my kneecaps, you need the instrumental case of Češky, and that will appear only if you have a corpus of 50 million sentence pairs. So you have to collect that much data to be able to propose the translation s Češkami, co je s mými Češkami. Yeah. So now, what was the proposed solution? And that is the extension of the phrase-based model. It's called the factored phrase-based model. And the idea is to separate the translation of the word itself from its morphology. So instead of translating directly the word form, we'll be translating the lemma to lemma, and then the morphological tag to the morphological tag. And we end up with something which the final user doesn't like to see, the pair of lemma and morphological tag. But we can use some morphological module or a generation step in the system, as we'll see in a second, to figure out what is the correct form. And the benefit here is that this generation step can be trained independently of the parallel data. So this is something which can be extracted from just a monolingual corpus, and that will give you the benefit of producing even the instrumental for kneecaps, something which was not available in normally sized parallel data. So this factored phrase-based MT can be formalized as a sequence of mapping steps. The mapping steps or translation steps, the mapping steps translate phrases of source factors to target factors. So one of them is obviously mapping the word form to word form, like 2 green, 2 zelené. Then we have the generation steps, and these generation steps somehow produce new factors on the target side from already known target side factors. So here we see things like dvě can go to feminine noun and dva can go to masculine nominative. So that's like tagging on the fly. This generative model will know what tags are possible for a given word form. These generation steps ensure the vertical coherence in this simple schema. So they ensure that the words are selected so that the form is in line with the tag that somehow came from the source and with the lemma that is also that was created with the mapping steps from the source. And then we have the normal component there as well. That's the target side language model that ensures the horizontal coherence, as we already know, like the coherence in the sequence of words. But now this can be applicable not only to the first factor, to the word forms, but we could have another language model applied to the morphological tags. So here is an illustration how that goes with the kneecaps thing. On the source side, we have the kneecaps. That's the first element in that vector. And we first morphologically analyze it. So we will know that the lemma of this, the lemmas of these two words are knee and cap. And also we will know that the first word is as an adjective and the second word is a noun in plural. And we have this sequence of processing steps that was predefined by the author of the system. And that sequence says that first translate, then generate, then translate, and then generate to arrive at the final thing. So let's go into the details. The first translation step translates the lemma into lemma. So the target side, again, a three-factor word, is still very much underspecified. But we already know that kneecap is Češka. That is the lemma, the base form of that word. But we don't know its word form in the final sentence, and also we don't know the morphological tag of that. Then we can use the generation step. This generation step is based on the monolingual corpus of the target side, and this searches in what all morphological tags can I possibly produce that word. So it will know from the monolingual corpus that Češka can be put in singular of the nominative, singular of genitive, and all other cases, and then in plural, singular, and genitive, nominative, all the possible tag combinations that are valid for this lemma. Then, when we again console the source sentence, so we will use a translation step that compares the source side morphological tag with the target side morphological tag, and we know in the source that this was a plural, so it will be much more likely to use plural on the target side as well. And it is not indicated here in the picture, but these translation options, these candidates, are actually obviously scored. They have some score associated with them, and they are sorted according to the score. So at this stage, the ordering changes because the plural, all the plural candidates become much more likely than the singular candidates. There are counterexamples. For example, in Czech, when you say in Czech, the police investigate, then in Czech we would use singular, whereas in English the police serves as plural. So the singular and plural are not always in line across the languages, but in general, probabilistically, the tag will be in relation. There we have created many more options. And then we can use the final step, the generation step, which takes the morphological tag and the lemma, and it produces the correct, the particular correct form of that word. And this is again based on the monolingual data only. So it has the capacity to produce a word form which was never accessible to the parallel data, or was never seen in the parallel data. So this is one way to think about this, and I'll just hint it now, and you will see an example of this later. One way to see this is to see it as the sequence of joins of SQL tables. And instead of having one table which lists the word forms in source language and target language, you have now two separate tables, one that lists all the translations of lemmas to lemmas, and that's shorter. And you have another separate table which maps source text to the target text. That's again shorter. And you do a product of these two tables. You do a join. And you also have these tables that check the vertical coherence, the generation step, to check the validity of combining a particular lemma with a particular tag. So this sequence of joins that has varying complexity, and you know that in databases you you search for the optimal order of joining tables. This happens here as well, but this search is not automated in any way. It's up to the author of the system to put the generation and mapping steps in reasonable order. If you screw it up, if you do a wrong ordering, if your data is not the way that you think, what happens is that you will generate too many candidates in one of these stages. You will have to prune them to keep them in the memory, but you're pruning them without any context, and you will lose the good ones. So the idea is to do this join of tables in a way so that the lists of candidates do not grow beyond the capacity of your system. By changing the order, you can reduce the memory complexity of the join operation, so to say. So again, let's summarize it. So factored phrase-based NT model is an extension of the phrase-based model. Phrase extraction, the standard procedure, is used for the mapping steps. There is also the extraction for generation steps that simply observes the monolingual corpus and sees how often a particular word form was with a particular tag, and then there is the decoding. And we'll go over the decoding and extraction in a second. This fits very nicely to the log linear structure of the phrase-based model that we have discussed in the previous lecture. Each of these steps simply brings in new features. So you will score your final translation, not only how good was it in terms of n-grams of the language model, of n-grams of word forms, but also how good it was in terms of n-grams of morphological tags, n-grams of lemmas if you wish, and also all the phrase translations, how well was it translated considering the lemma sequences of the source and target languages, how well was it translated considering the morphological text in the source and target languages. These weights, so there will be more components, and weights of these components can be again trained by the minimum error rate training, except that it will have a harder time because there will be more features to consider. So how the extraction is done, that is very straightforward. So as a reminder, phrase-based MT is based on these word alignments, and you extract phrases which are consistent with the word alignment. So from this sentence pair, you learn that natürlich hat John can be translated as naturally John has. If you want to extend this and use also the morphological text or part of speech text, you simply replace what you are observing, the word forms, with the linguistic annotation that you are interested in. And there you will learn that if a sentence starts with an adverb, then in German, the verb goes second and then comes the subject, while in English, the subject is still the first and the verb is the second. So here, by considering not the exact words, but instead they're part of speech tags, the system has some explicit knowledge of syntactic patterns. These are short distance syntactic patterns only, but they can be helpful for these reorderings, such as adjectives put after nouns in French and or this example. So here is again the benefit of using factored models. We have a corpus of two sentence pairs. One sentence pair mentions an old man in the accusative case, and the other sentence pair mentions black dog in the dative case, černému psovi. And normally, what you would do, you would focus only on the forms of these words, and you would extract the phrase table, the table to work with to the database that contains the fully inflected word forms. So you would know how to translate starého pána, old man, and you would know how to translate černému psovi as black dog. But what happens if you break it up into these two steps, as I suggested in the previous? You will extract separate phrases, separate tables. One will be for the lemmas, and that will allow you to translate starý pán, whatever the form is, as old man, and černý pes, whatever the form is, as black dog. And separately, you will be learning that you can translate either accusative or dative to the sequence of an adjective and noun in English. So the benefit is exactly this. You can use a combination of lemmas and morphological text that was never seen together in the parallel data. You can use the accusative knowledge from the old man phrase and the lexical knowledge, the black dog, from the black dog phrase. That's the increased robustness that you have gained with this factorization. So now let's look at the slides which essentially come from what Philip Ken has presented at MT Marathon more than 10 years ago, and that's the decoding, how to translate with this model, and then some experiments with that. So again, as a reminder, with phrase-based MT, you have this input sequence of words, geht ja nicht nach Hause, and you translate, you first consult your phrase tables to see what are all the possible translations of these phrases. And you consider the longer and the shorter ones. And there is some selection of those which are the best. So that's what you use. That's what you search for in the search. So you are starting with the empty hypothesis, and you are going further, adding covering words from the source and appending the current hypothesis with the words in the target. The final choice will be the path which covers everything and has the overall highest probability. With factor decoding, this search remains the same. What is more complex now is how we create the translation options. So the hypothesis expansion is not according like a single lookup in a simple table, but it is constructed in the sequence of mapping steps. we can translate the lemma to lemma, the morphology to morphology, and then generate the surface form of the target site using that. So here is an example which the source word house is translated into houses or homes or buildings or shells, and all the other parts or the other factors help to construct the correct word form. But they are built using the join operations of the SQL tables, if you want this analogy. The good thing is that all these processing steps can be pre-computed. So you can run this join of tables already in the stage when you are considering what are the translation options for a given phrase. So you pre-compute it once when you're creating the translation options table, and then you simply use these more verbose translation options in the search. So the search remains identical. There is no change in the search at all. What is different is how the translation options are now constructed, and they are constructed on the fly. So there is many more of them. That's the hard part. So the translation options explode because you multiply all these tables. Originally, only 20 translation options per span were considered, and now you can easily get to thousands of possible word forms. So that's the morphological richness now demonstrated or run into in the real time. So you need to prune again. You prune it, select only the best candidates already during the preparation of translation options. And this is exactly the place where you need to think carefully about the joins operation and the memory complexity. If that grows too far beyond the pruning limits, then you will be dropping possible translation options that will be necessary, that would be necessary for the correct wording of the sentence. So you are like limiting the capability of the system. You're dropping some of the candidates without knowing the context in which they will be used, and that is bad. So here are the experiments. The very first and simple setup is to translate forms into forms and then do part of speech tagging on the fly, so to say. And that allows you to use a 7-gram language model on the part of speech tag, enforcing some syntactic structure over the sentence. That was one of the main problems of phrase-based MT, to have some overall understanding of the sentence. So this is not a solution, but it is a partial remedy of that problem. And indeed, when tested on English-German or German-English, it increases the Blaise score a little, because the overall fluency of the sentence is better. Also, the Blaise score, remember, it is limited to 4 grams only. So it is probably not so sensitive to improvements in this respect. I think that human judgments would be more happy, would show a better increase than the Blaise score, which is limited to 4 grams. An improvement of this is that you consider not only the part of speech tag, but also the full morphological information. And that is exactly the thing that we have discussed at length beforehand. The combination of a determiner in, well, singular and a noun in singular is good. But a combination of determiner in singular followed by a noun in plural is a grammatically wrong sequence, and you should avoid it. So this is what the language model over the morphological tags should allow you to remove, because it will be trained on all possible determiners and nouns, and it doesn't have to relearn this knowledge of agreement for every combination of a noun and determiner. And this is the motivating example. We said that it may be better to translate the lemmas to lemmas, like kneecap in any form into češka, and then part of speech tag into morphology and part of speech tag, and generate the final word form based on that. So that's the linguistically motivated thing. Now how does that work? So the baseline was 18 point something Blaise score. We have seen the improvement with the part of speech model in the previous setup. And then we've moved to the linguistically adequate morphological generation model, and the Blaise score dropped by 5. So how is that possible? The problem is that we are introducing independence assumptions where they don't have to be introduced. Sometimes you need these independence assumptions because you don't see kneecaps in all the cases, but there are many words which you do see in the correct cases, and you can directly copy the correct word form, and you don't have to do the decomposition into lemmas and tags. So these additional independence assumptions bring an information loss, and therefore the translation quality drops. So here's the solution. The solution is called alternative decoding paths, and you essentially combine the two models to operate at once. So you let the system do the normal word for word, like form for form translation, and you also consider the other path, the lemma and part of speech being translated independently, and the fun for being generated from lemma and the morphology. These two components will bring in separate features that each will get some weight in the minimum error rate training, and on some held out data set, the minimum error rate training will identify how often on average should it trust the direct path, and how often on average should it resort to this separation of the lemma and the part of speech. And that is exactly what needs to be done. The system is now flexible. It can do the backoff to the separation, to the independence assumptions if needed, but it has also the original full power of copying what it has known, what it has seen in the data well. So if you do these both paths, then you do get the improvement that you wanted. You are improving over the baseline by far. In some cases, for some language pairs, some information is missing in the source, and you need to add it somehow. And you can extract it monolingually on the source side. So one such example is when you're translating from English into German or English into Czech, you need to identify the case for noun phrases. And if you're translating from Chinese to English, you need to guess even the number for nouns. And when you are doing some pronoun translation, again, you need to figure out what they refer to. So this additional information can be extracted from the source side alone. And here's an example that was tested on English to Greek translation. A similar setup would work for Czech as well. On the source side, you analyze the sentence and you check whether a particular noun serves as the subject or serves as the object in the sentence. And this information, subject versus object, is a very good indication to whether it should be translated as nominative or accusative in the target language. So here the translation table, the mapping table from the role or function of the word in the sentence in English into the case in the target Greek, that will contain mappings like subject goes to nominative and object goes to accusative. There could be again swaps, changes in the case, but the data will have sufficient statistics for that across all the visible, across all the nouns and all the subjects and all the objects in the data. It is not learning that for each individual word form. So this is an illustration. You parse the source sentence and you traverse the tree so that you, based on the position of the word in the tree, you know whether it sits in the subject position or the object position, and that will imply then the case for the translation. And here's a summary of various evaluations. Indeed, it helps. So that's a good thing that we can use explicitly available linguistic information on the source side and improve predictions on the target. So let's now discuss Czech in detail, because these are experiments that I've worked with for quite a while myself, and I examined more setups. So the vanilla setup that we have here is to translate form to form and apply a single language model. Then we have a setup which I call translate and check, and there we translate the form of English into form of Czech, and then use the generation step as a tagger on the fly. So for every word form, the system also tries to identify what is the morphological tag of that, And the benefit, so there is this extra cost, you are tagging the words as you have already produced them, but there is the added benefit, you can apply the second language model there. So you have one more language model. And this check can be done twice. You can check not only the coherence of the sequence of word forms and the coherence of sequence of part of speech text or morphological text, but you can also check the coherence of the lemmas. And this is like a preparatory step, but reversed yet, to the linguistically very motivated one that we have seen with the alternative decoding paths. You can translate the lemma to lemma, independently translate the morphology to morphology, and then you combine the lemma and morphology to the final word form, and this is what the user wants to see. And you again have the capacity of applying 3 language models to check the coherence of each of these independent streams. So one thing that you have to realize, I've already hinted that, but when you are doing this tagging on the fly, this additional translate and check step, the target site morphological text actually increase the complexity of the search. We have seen that words are morphologically ambiguous, so that means that some of the words, some of the word forms can serve in multiple cases. And if you are operating only with the word forms, then there is no reason to like separate these cases. The system is learning on the fly that some of these word forms fit well with other word forms. So you are not deciding whether it was accusative or whether it was nominative. But if you are introducing this extra factor with morphological text, then suddenly for this candidate zelené pruhované, you really have to spell it out. You have to say that zelené can be genitive, dative, or nominative. And this zelený, that has only one option, luckily, but you have all the full details here. So the number of translation options will increase immediately as soon as you add this explicit information. The ambiguity was collapsing the part of the search space. So there is a trade-off. You are complicating the search, but you are also giving yourself the power to select the good combination based on the more dense statistics of the morphological text. And this trade-off has to be well balanced. If the trade-off is not balanced well, if the complexity grows too much and the language model on text does not like make use of this, then you are going to lose translation quality. So here is a summary of what the results were in 2009. Before looking at the outputs, I'll actually summarize how it went across the years. So in 2007, the translate and check was the best setup because we had relatively small data, but already like big enough so that the linguistically adequate path would not be the best choice. Then a year after that, the translate and check setup was still worth the effort. But in 2009, our computers were already like fast enough and we had large enough disk space and large enough data so that we could handle 7 grams of forms, word forms, and not 7 grams of part of speech text only as in the previous years. So in 2009, the best result was actually achieved with the vanilla phrase-based system, and the translate and check system was already a little worse, and that was because the added complexity of the search space was not then compensated with sufficient gains from the language model. The language model on word forms was good enough to make the decisions. In the previous years, the language model on the word forms was unreliably estimated due to smaller data and slower machines and like smaller language models. So in previous years, it was worth the effort. With larger data, the baseline was better. And the setup of translation translating separately the lemma and the morphological tag, and then generating the form, that was too big. It simply exploded. With the larger data, there were too many possible words and too many possible, like all the 2,000 observed morphological tags, and that Cartesian product of words and the text then exploded. So it was not possible to train this setup with the large data that we had, the 2 and 2.2 million sentence pairs. I used only much smaller data set, and there on this smaller data set at runtime, the search was too complicated, so it actually got lost in the search space, and the choices this linguistically adequate decomposition made were worse than what the phrase-based system did on average. Yeah. So here is the explanation why it failed. So the factored models are synchronous, and that means that all these translation options that now have the lemma and the morphological tag have to be first fully instantiated. You need to populate all the output factors. Everything has to be specified. There is no room for underspecified translation options. And then you enter the main search. And in the main search, that's only then you are putting the translation options next to each other. But it is only when you are putting the translation options next to each other where the language model can check which of the morphological tags are in line with what. So if you are translating the noun and the adjective separately, and you are hoping for the language model on the morphological text to select the good combination of cases between these two, then you need first to consider all the variations of the adjective, all the variations of the noun, fully instantiate these, then in the main search put them together and select the good combination. And if this doesn't fit into your memory, if your like pruning limits are too strict, you will drop some of the less likely individual noun forms and individual adjective forms, and you have removed the combinations that the language model would be searching for. So that's the key reason that you are pruning the translation options before the linear context is available. There was an attempt by Yu Huang to work on asynchronous factors, and that was too difficult to put together to like structure the search, what should be explored first and what should be explored later. So that didn't really work. And what I did in another decoder of completely different nature was to use delayed factors. So there, in my configuration, I said, okay, I know that there will be too many possible cases for this noun. So let's not figure out the case now when we do not know what the verb nearby is or what the noun nearby is. So these delayed factors actually say that during the translation options phase, you leave some of these factors unspecified, and only then after the main search is done, you will use the information from the neighboring words to fill the missing information. And then obviously you have to do the final processing steps, such as finding the correct word form given the word and its case. So that was the unfortunate linguistically adequate setup, which didn't work with synchronous factors. And what worked very well in many years was this translate and check setup. But I mentioned that in 2009 there was the gain from the translate and check was limited, and that was limited with if I had only one language model. So the setup that I had in the last years of phrase-based MT, and that did help with this translate and check, was to use several language models of different type, and that is something that I would like to share with you because that's useful. We have these two output factors. We have this output factor of word forms, and we have this output factor of morphological tags. And we have parallel data and monolingual data. All the language models can be estimated on the monolingual data. Depending on what factor we look at, we can afford various lengths of the n-gram language models. So in my best system in the last years of phrase-based MT, I actually used 4 language models at the same time, and each of them was reliable for other parts of the sentence. So one language model was called long, that was based on the word forms, and that was the 7 grams of full word forms, and it was trained on like 700 million tokens. I could not afford to use more data in this language model because then there would be too many 7 grams and I couldn't fit the language models on the disk. But I had more data. I had actually almost 4 gigawords of Czech texts. So with those, I trained a model which I call big, and that was only 4 grams. So this language model had like smaller span. It didn't look so much around, but it had these 4 grams estimated very well because it was trained on a large amount of data. And then I had morphological texts, which were even longer. I could afford 10 grams of morphological text and even 15 grams of morphological text. The 15 grams are sparser, so I added them only like later. And here you see what is the blast score if you use the various subsets of these language models. So the basic setup is to use translate and check. The basic setup actually is just to translate and use only the the model based on word forms, the 7 gram of word forms. Then using 4 grams is actually better if the 4 grams are estimated on very large data. Then the long and morph together give you a little bit of improvement, and the big, long, and morph is the best setup, and then you can still improve a little if you use the 15 grams of morphological text. So each of these language models has a different view on the output sentence, and each of them is estimated with a different confidence or reliability. So using all of them and tuning their importance using a held out set is the best thing that you can do. Yeah, so here's a tentative summary. I'll still go with some more details. So there is the target site rich morphology that causes data sparseness. Factored setups allow you to compact this sparseness. So instead of one big table, you have 2 separate tables and you do the join. But if you do the join in a wrong way, it can very easily explode at runtime. This explosion can be contained if you prune it, but then the pruning happens without linear context, so there is very high risk of search errors. So we'll now cover 2 techniques which try to handle the sparseness, but still avoid the explosion. One of them is called 2-step translation, and the other is called reverse self-training. So the 2-step translation builds upon the idea that you can separate the lexical translation and the morphological generation in a language which is as complex as Czech. So in the first setup, let's train a normal phrase-based system to translate from English into lemmatized Czech. And we know from the very first slide that there is like very comparable number of lemmas in Czech and in English. So this will not be too bad. There will not be the combinatorial explosion, the complexity of the Czech language. The Czech language will behave nicely. It will be like morphologically poor. And we designed this lemmatized Czech so that some information which is already available in English is not lost. So for example, here this translating after a sharp drop, we know that this drop is a noun and in singular. So in our middle language, kind of lemmatized Czech with improvements, we will translate it into pokles with these details attached here. And these details say, well, it is a noun in singular, and also it is an affirmative, it's not negated. So this information is already available in the source, and let's not lose it in the middle language. So the first step is responsible for all the reorderings and all the changes of number of words for various phrases, so it can handle the differences in number of words. But it is not cluttered with the decisions about the case. So Then we have to apply the second step, which converts this simplified check to the full check. And that is trained on much more data because it can be trained on monolingual check data only. You take a large corpus of check and you simplify it. So there's like a back processing. This way you create your synthetic parallel data and you train the normal system to go forward from the simplified check to the fully inflected check. And this step, because there is already the richness of check, is limited to proceed with word-for-word translation. So phrase max length is 1. And also, it is not allowed to do any word wordings anymore. So it's monotone. And that way you can afford to extract the tables from the huge monolingual data that we have for check. So here's the summary. If you apply this setup on a small parallel and small monolingual corpus, then the Blaise score and another metric that we used, semantic pos, that was kind of checking whether the content words are there, whether all content words are there regardless their forms. Both these metrics have an improvement from vanilla to the two-step setup. So there's the 2 arrows at the end. If we use a small parallel corpus and a large monolingual corpus, then Blaise score is already like not sure. Blaise score decreases, and it says it is better to use the vanilla setup, while the semantic words counting is still improving. And here, I think that the Blaise score is probably happy about the nice 4 grams of check, but it is not so sensitive about words being dropped, as we have discussed in one of our previous lectures. And as could be expected, if you have large parallel data, then both metrics will say it is better to use the simple translation and not this two-step separation, because again, the two-step introduces some independence assumptions and that are not always needed. So you are shooting yourself in the foot when you are making these assumptions. So we also manually evaluated this interesting setup, which used small parallel data and large monolingual data. And there, the conclusion was that we had 2 annotators, and each of them slightly preferred the two-step setup. But they didn't agree on which sentences it was better. So it's like unclear whether this two-step setup is worthwhile if your monolingual data is large enough. So now the reverse self-training, and that is something which is more successful. So the idea is that you have this translation model and you have this language model. And the language model, now when you use the clever techniques and you train on text and things like that, that will allow you to select the good combination of the word forms. But if the translation model doesn't propose these forms, then you cannot select the right form anyway. So in the first place, your translation model has to propose the word forms to consider. And the translation model is based on your parallel data. So how do you get these needed word forms in the parallel data? And that's where the reverse self-training comes. This is something similar to the back translation technique, which is very successful in neural machine translation. But in phrase-based NT, you have to help it a little. So the idea is that you have a small parallel corpus that illustrates how the word cat can be translated by 2 sentences. A cat chased, kočka honila, and I saw a cat, viděl jsem kočku. Because of different roles of the cat in the sentence, the Czech word forms differ, kočka and kočku. And in our monolingual data, we can see that we can also have other word form of this word. In the phrase četl jsem o kočce, we have one more thing that we would never be able to produce with our existing system. So what do? How could we create the source English for this phrase? How could we synthesize the source side and include this monolingual data in our parallel data collection? Well, if you translate it directly, then kočce, based on your small parallel data, would be an unknown word. So it would become I read about kočce. So that is of no use. We would not learn anything useful. But in the reverse translation, we can back off to lemmas. We can use Czech in the lemmatized form, and we know that the Czech lemma kočka will be translated as cat, and actually in all cases. So here the same thing will hold. In English there is not the distinction of cases. So we will train a reverse system that backs off or relies also on the lemmas. It will not know how to translate the form kočce, but it will know how to translate the lemma kočka because it has seen kočka in these two sentences. So it will translate this sentence, četl jsem o kočce, as I read about a cat. And now you include this in your parallel data, and that's the benefit that you get. You are learning a new phrase about a cat, o kočce. So this is you are learning a new form of a noun word, and you are extending the translation model to be able to offer the forms that the language model will then happily appreciate. If only your language model was clever, you could not get the benefit. So the technical way how to do this is again use alternative decoding paths for the reverse step. And instead of translating only form to form, kočce into something unknown, we can resort to translation of the Czech lemma, kočka, to the English form. So it is then like making up the English side a little. It is guessing the form of the English word, but English is morphologically poorer, so it's okay to do this guess. There is no much errors involved, and you create the synthetic parallel data and you train on those. For us, you would have to apply other linguistic expertise. So when you were doing this for English into German translation, in the reverse translation step, you should split German compounds. And if you did this for Turkish, you should simplify Turkish by dropping Turkish morphology in a way that is appropriate for Turkish, not just this lemmatization. Yeah. So here is how that helps. If we have fixed parallel data and of a small size, then it is known that using a large language model will help. So the monolingual data, as it grows, you are getting higher and higher blast scores because your n-grams are estimated more reliably. So this is the situation where your translation model is not offering the word forms that the language model would appreciate. The translation model is limited to the small data. If you use the increasingly large monolingual data with this reverse translation trick, and you include all the word forms that appear in the monolingual data also in your translation model, then you get double the increase. So that's the clear benefit. Unfortunately, if you are also collecting real parallel data, then very soon there is not much benefit of this approach. So it was extremely useful if you have less than 1 million parallels, less than 500,000 parallel sentences. If you have about 1 million, it is still helpful. But from 2 million of parallel sentences, there is no benefit from this reverse translation trick. So that's different from the neural models and the back translation, which is still effective even with very large parallel data sizes. So let's now look at morphology in neural machine translation. So we have already hinted this when we were introducing the neural machine translation. There is the word embeddings tables, and you cannot make these tables too big. We know that the phrase-based MT already struggled with productive morphology when we have around 1 million or more word forms, such as these compound words or very large number of morphological variations of words. The neural MT with its embedding tables can fit at most 30 to 80,000 different word forms. So for this reason, immediately words had to be broken into some things, and we can go for syllables and or morphemes as two examples of linguistically motivated separations or segmentations of words, and then we can go to something which is like technically motivated, character pairs or individual characters, and then something that we will illustrate on the next slide is that's called bipair encoding. That is a combination that is based on compression algorithm. It simply creates the dictionary of known word forms so that the most frequent words are there and less frequent words are broken into smaller parts. So given a dictionary of token types and frequencies and their frequencies, you are trying to come up with a fixed size dictionary that will contain the frequent words as wholes, and that will break longer words or unknown words into more units, and these units of themselves by themselves should be also like the most frequent. The way of constructing this dictionary is that you repeatedly identify which character pairs are often seen together. So you replace the most frequent character pair with a new unit, and then you repeat this this merge operation. So if we have this vocabulary, and it's important to realize that this vocabulary actually comes with frequencies of these words. So it's like a frequency list, and you are counting each character pair depending how often the word was also seen. But let's assume that each of these words was seen exactly once in our corpus. You will check which of the character pairs are frequent. So low was seen twice. We was seen 1, 2, 3 times. ER was seen 1, 2, twice, and so on. So the most frequent character pair in this example is indeed this we. And for this reason, you decide to merge these two tokens together, these two characters together, and you introduce a new unit to your vocabulary. So in your vocabulary, you started with the list of letters, and then you are adding a new letter which has the shape WE. You replace this pair of characters with this single new letter. So your corpus now looks differently. You have L, O, we, R, so four characters in this word and so on. And again, you scan for the most frequent pair of characters. And here, the most frequent pair happens to be this we followed by R. So this is a new merge operation that you introduce in your like in your setup. You know that you will. It is useful for the compression of the text that you are training on to treat this we, E, R as a single unit, because it is a unit that comes frequently, up frequently. And you proceed. The next merge will be probably, yes, this ST. So ST goes into this single character ST. So you end up with this sequence of merges. And then when you apply this to the new input, you simply apply it in the order in which it was created. So when you are then compressing or processing with this byte pair encoding the word newest, you first merge this we, and then you merge this st, and then you are at the end of your merge operations list. So you end up with this sequence of translation units. The first one is just the letter N. The second one is just the letter E. Then we have this unit WE, and then we have the ST at the end. So the vocabulary size will be as big as your alphabet and the number of merge operations. And this is something which you control yourself. So you can stop whenever you like. And whatever is not merged any further, that will simply remain represented as the subword with the subword units. So for our machine translation system, the input is now not a single token newest, but it is a sequence of 4 tokens. But it is designed so that frequent words will have their own unit, and less frequent words will be broken. Even maybe in if their stems, if their base meaning components are frequent enough, then there could be like a stem part and the ending part, and there the neural MT will get the capacity to learn that stems should be translations of something, and then the endings come from our other indications in the sentence. So this separation of subword units is actually sufficient. All the complex things that I've discussed for phrase-based MT throughout the lecture have been totally superseded by the neural MT and the subword units. Neural MT simply learns by itself what is the correct combination of these subword units, and it gracefully handles all the morphological richness of Czech. So when people who were never did any phrase-based MT came to machine translation and came from the neural MT area, they said that neural MT is complex, is conceptually simpler than phrase-based MT, and I have to agree with that at this point. Indeed, you don't have to care about morphological richness. The model will learn it for you just by observing sequences of subword units. So there are a number of flavors of these subword units. So we have discussed this byte pair encoding by Rico Henrich. There is also Google word pieces, which were introduced for speech processing around the same year. And then in Tensor to Tensor, which was a popular implementation of the transformer model, there was another implementation which was called subword text encoder. And the current best or currently most commonly used implementation is called sentence piece. And again, each of them has slightly different processing. So we tried once to compare them as well empirically. So we've applied STE, the subword text encoder, and BPE, and we've observed an interesting thing. STE has always added an underscore at the end of the word. And that had the positive effect that for Czech, where you have, for example, the word tramvaj, the ending can be separated from the word, even if it's like an empty ending. So we have 2 sentences, blíží se k tobě tramvaj and z tramvaje nevystoupili. And these 2 sentences, when processed with STE, which appends these underscores, will share the unit tramvaj. And this sharing of this unit, the fact that you observe the word tramvaj, the token tramvaj, in both of these sentences, give the model the necessary generalization power. So it will know that tramvaj now is something which approaches people, and tramvaj is something that you can get off or get onto. And this knowledge allows the model, the identity of the token allows the model to realize all the similarities and the behavior of the word. If you use the BPE in its default variation, blíží se k tobě tramvaj, z tramvaje nevystoupil, then unfortunately there is no way to separate an empty suffix. BPE indicates unfinished words with these double ampersand, the double @ signs, and the nominative was observed frequently enough, so that becomes a single word in the dictionary. But this other case was not observed enough, and it happens to be broken into 2 components. And here the model does not see the same unit, so it has no way of finding out that tramvaj with tramva. So here the identity of the word is broken. If we add the underscores before processing the corpus with the BPE, we give BPE the same capacity, and we can be lucky now. This tramvaj will get the ampersands as an unfinished word, and it will be the same token regardless whether the ending was empty or whether the ending included a single word. So this is something that we've figured out only empirically, because it's like tedious to read the source code. It's easier to look at the data and try to figure out why one of the methods is better than the other. In our German to Czech experiments, we tried this underscore trick, and we found one more interesting thing. It helped, so adding this underscore to every word did indeed increase the blast score with BPE a little. But if we added the underscore after every word form, every token, except for the final full stop, then it helped much better. So the best technique that we had for this particular language pair was to, well, the best one was actually the subvortex encoder from tensor to tensor. But BPE could get almost to that performance if you added the underscore at the end of all tokens except for the last one. And what we haven't searched for further is whether this is because we have changed the counts with which the underscore was observed so that the BP learned different words, or whether this indication of the last word token was actually helpful for the subsequent translation model. So this is something that could be still investigated, but the increase in the blast score was amazing. So one message to take from this is that the very tiny details, such as adding an underscore at the end of every word, can suddenly very dramatically change the performance of your method. And it's always worthwhile to do these simple variations if you get the idea that you should do them in the first place. Yeah, so there is still quite some room for linguistics. Some linguistically adequate separation of like stems of words and their endings was carried out in this work, for example, for Turkish and I think more professors for Finnish. And it was measured to be better than BPE. Then Matthias Hook looked at English-German translation, and again he did a fair bit of rule-based, like linguistically motivated compound splitting and suffix and prefix splitting, and he figured out what is the best combination for that particular amount of training data and language pair. In our German to Czech setups, we tried unsupervised linguistically motivated segmentation of words, and also supervised based on a derivation dictionary of Czech word forms. But unfortunately here, the subvortex encoder worked best. So this is it for today. Let's summarize. We have seen that rich morphology causes serious problems to any token-based machine translation systems. We have discussed this in very much detail in factored phrase-based MT. So these factors allow you to capture this additional information, and they also bring in immediately the risk of search errors because the morphological information brings in distinctions. That's what linguists are paid for, to notify you, to warn you about possible distinctions. But if you introduce a distinction and then you do not make use of that by applying a language model which generalizes better on these morphological text, for example, then you are only increasing the complexity of your search space, and you are not counteracting that with any cleverness. So before adding any attribute, before adding any explicit distinction, you need to think twice, and you need to make sure that you avoid data sparseness. You need to provide backoffs. You need to have the alternative decoding path, which works with the original word forms that that are not subject to the independence assumption, and if you are like making your models excessively complex, you will really have troubles optimizing them and making them work, because the search space will be larger, and the complexity is in the system, and you have just moved it from the lack of data to the size of the search space, and the search space is constructed dynamically, so it's hard to explore. You can explore it only through debug prints. If you have the complexity like written down in the data, you can easily browse it on your disk and you can understand it immediately. If you leave it to runtime, then you are risking very much that you will not notice there is some horrible complexity going on, because machines are fast these days. So it's actually useful to print out everything what the system is processing, because there you realize how like stupid decisions or how complex the search space for the system is. And we have discussed the reasonably promising two-step translation, where the lexical translation was separate from the morphological translation. So the morphological variation was added only in the second step by changing word forms and keeping the output sequence monolingual. And the better setup that we did was this reverse self-translation, and that was very good for small data, and it was not harmful for large data. So this reverse reverse self-training setup was actually the best way of handling the complexity of the language by storing it, writing it down to the data, and then using your normal baseline approach to like digest it in its best possible way. So this is exactly, the reverse self-training is exactly the move back from the complexity within the search to the complexity in the data. But now the data is clever and the data demonstrates better the complexity so that the original system can learn it better. And neural MT was quick. Neural MT just handles morphology well. It's subword units, and that's all you need. We have described in detail the byte pair encoding. That's one of the options. But there are other options, and also it would be very interesting to link these subword units to the linguistically motivated subword units. Yeah, okay, so that's it for today, and next week we'll talk about syntax in statistical machine translation, and then we'll come back to neural MT in 2 weeks from now. Thank you. Yeah. Yeah, so let's take a break. I'll quickly check if you have any questions, and I'll stop this video recording and I'll start another one, and I'll put the link to the Google document if you wanted to follow. But as said, it's maybe better to follow the lecture only next week. So, questions, no questions, and we have amazing, great. We have 6 students, that's perfect. Yeah, so thanks for watching. If you still have any questions afterwards, please tell me. And otherwise, speak to you in 10 minutes or 15 minutes, or speak to you in next week from the recording. Thanks, bye. No, já teď bych si skočil určitě nahoru.